All right, guys, happy Friday. We are back again with some more circle theorems. And so, yes, you know what that means. It means we're doing some more labs and some more proofs. And you guys are very happy. All right, so go ahead and get out your calculators. We're going to be doing some theorems involving the lengths this time of chords, tangents, and secants. All right, so I know you guys are getting bored of doing theorems involving angles. So we're going to spice it up. Now we're doing some theorems involving the lengths of chords, tangents, and secants. All right, so we've done a whole bunch of angles, like inscribed angles, central angles, angles formed by two tangents on the exterior, formed by two secants, right? A tangent and a chord. So we've done a whole bunch of angles. Now we're going to be taking a look at the lengths of these guys. So this first lab is fairly simple. If you want a preview of it, stick around for another minute. Otherwise, pause the video and you can try it. But basically in this lab, right, you're just going to be constructing a circle. You're going to be making two chords, right? So chords could be anywhere, right, as long as the endpoints are on the circle. You can even make a diameter, right? Diameter is a chord. And you're going to mark the point of intersection, and then you're going to measure 1, 2, 3, 4. You're going to measure the 4 segments formed by those two chords and see if you can figure out the relationship. So this relationship is not the easiest to see, so you might need to play around with the numbers, but try your best. I'm sure you could figure it out. All right, so for the 3 of you that are actually doing this on your calculators, go ahead, give it a shot, and I will start mirroring my sketch pad, and I'm going to do it on here, be a little quicker. All right, so if you're doing a slab, hopefully you have a circle. You got chord number 1, chord number 2. I did not get endpoint on the circle. And you mark the intersection point with a point. And let's start measuring. So measure from there to there. That length, AB, 3.77. Let's measure BC, 2.17. Measure, is that going to be BD? Measure that. And let's measure this last segment. Yeah. All right. So like I said, it's kind of hard to see the relationship, so if you don't see it, that is fine. But maybe some of you played around with this enough, and if I multiply, let me calculate, let's say, AB times BC. Right, so I multiplied the 2 segments of that chord, and I get 8.17. So what do you think is going to be equal to 8.17? Well, 5 times 1.6, that's 8. That's really close. Let's try multiplying those 2 numbers. So if I calculate this times that, oh, very nice. All right, I knew you guys did not expect anything else, and that's right, they are, okay, never mind. They are equal. So, as always, I can move these endpoints around, and look, it stays the same. Wow, I got a nice number, 10. All right, 2.5, I don't even know what that is. All right, 2.5 times 4, right, equals 2.13 times 4.7 is approximately also equal to 10. So, there we go. Now we got the relationship for our first theorem. So let me get back to my iPad and let's write down our discovery. All right, so if 2 chords intersect within a circle, what we saw is, bam, I wrote this down earlier because it's quite a bit, but we saw that the product of the measures of the segments of one chord equals the product of the measures of the segments of the other chord. All right, so I know that is a mouthful, but the concept it's saying is actually pretty simple. All right, it's saying, well, let me label the points here. Let's call this chord AB. And let's call this chord, let's say CD, intersecting at E. Well, that theorem is saying that AE, right? I think you guys can fill in the rest, but the product of the measures of the segments of one chord. So here's one chord AB, right? The measures of the segment of that chord are going to be AE and EB. So the product of those measures, AE times EB, is going to equal the product of the segments of the other chord, which are CE and ED. All right, so that's what that theorem is saying. Again, a lot of words, pretty simple idea though. So, of course, we've done the lab, we've seen the relationship, but we haven't proven it yet. So here is the fun proof time. So given chords AB and CD, which intersect at E, prove our theorem. So I can actually just copy and paste this picture because it's exactly set up the way this given is, right? We got chords A, B, and CD intersecting at E. And we want to prove, again, AE times EB, that times that equals CE times ED. All right. So I'm sure you guys can do this because, you know what? You actually did this for your test. This was the first question on your test, essentially. Essentially, almost. But let's think, if we want to prove AE times EB equals CE times ED, when is the only time you've proven products equal to each other? That's right. You guys thinking what I'm thinking? It's when we've done similar triangles, right? And we did product of the means equals product of the extremes. POM equals PO. So, similar triangles, that means I'm going to be using CSSTP, right, to set up that proportion. So what proportion is going to give us this product or this equation? So I know it's going to be AE over something equals something, right? There's our proportion, but EB has to go over there because when I cross multiply, that's how I get AE times EB. So EB is going to be here, which means I can make that CE and ED. So if I want to prove that proportion, which triangles do I want to prove similar? Well, I see, if you look along the top, I see letters A, E, and D. So that might be a good triangle to construct here. And I can make that triangle. I can also make this triangle. And if you take a look at these two triangles, these have all the segments required in a proportion. So in essence, we want to prove these two triangles are similar, right? So looking at that final statement, this is what we can surmise we need to do. And we just kind of work backwards. So we want to prove those two triangles similar. That's the main idea of this proof. So step one, write down your givens, right? Make sure you actually write them out, not like me. Step two, let's construct AD and CB. Construct AD and CB, right? Because between any 2 points, only one line segment can be drawn. Step three, so how do we actually prove these two triangles similar? Well, one thing we could do is, I see some inscribed angles. So angle A here, right? That's going to be half the measure of arc DB. But isn't angle C here also intercepts the same arc? So wouldn't you guys agree that these two angles have to be congruent, right? Because they intercept the same arc. So we can say that inscribed angles that intercept the same arc are congruent. Or if you want to do it a little longer of a way, you can say that angle A equals half of the measure of arc DB. Angle C equals half the measure of arc DB, and then you can use substitution, set them equal to each other. So we got a whole bunch of ways. But I'm going to go straight to the easier one, which is angle A is congruent to angle C, because inscribed angles that intercept the same arc must be congruent. Right, and I think that should make sense to everyone. And I guess we could do vertical angles now, right? That would prove another set of angles congruent. But couldn't we do the same thing for, there's that and that? Couldn't we do the same thing for these two angles down here, angle D and angle B, right? Because those also intercept the same arc, right? They intercept arc AC. So therefore, those two angles must be also congruent, and I'll save myself a step by just putting that under step 3 as well. So now that we've proven two angles congruent, that is enough to say the triangles are similar. If you want to prove those last angles congruent as well, go ahead, but you don't need it. So let's name our triangles appropriately. ADE. Triangle ADE is now going to be similar to triangle CBE. Right, by angle, angle. Step 5. Now we can say this proportion has to be true. Right, let's just double check. AE is to CE as ED. Right, ED is to BE. So that definitely checks out. Right, corresponding sides of similar triangles are in proportion. CSSTP. And once we cross multiply, we are going to get a proof statement, which is AE times EB equals CE times EB, right? And that's PO equals POM, or POM equals PO. And that's it. So pretty simple proof, to be honest, and something that you did 90% of on your test, because on your test asks you to prove something like this, right? So yeah, 5-step proof. So example 1, using the diagram above, if AE equals 6, EB is 10, and ED is 12, find CE. So pause the video, do it. I'll give you 10 seconds. All right, good. CE is equal to 5, right? Not even going to go over that. Unless you actually do have a question, let me know, but I think you can all get CE is 5. And that takes us to our second lab. All right, so lab number 2. Let's see what's going on here. And let me close and reopen Sketchpad so it doesn't time me out. So go ahead and read that lab. Here's a preview of it. You're going to be making a circle. You're going to be constructing 2 secants. So a secant intersects a circle 2 times. So let's say there's one secant. Here is another secant. And this time you're going to be measuring this distance, right? And that distance. Measure the entire length of both secants. So there's the entire length of the secant from the external point to the second intersection with the circle. So I'm calling that the second intersection. I know it's not very clear. And then measure the length of the external segments of the secants, the part of the secant that lies outside the circle. So that guy. All right, so in your calculators, go ahead and do that. There's not really any tricky steps. So let me switch over to Sketchpad and show you what that looks like. All right, so we got a circle. Secant number 1, secant number 2. And then just measure what I asked you to measure. So let's measure the entire secants. So there it is, 14.04. Measure this secant distance, right? If you were thinking these secants had to be the same, you probably were thinking of tangents, right? Tangents drawn to a circle from an external point are going to be congruent. And then I'm going to measure the external parts. There we go. And from there to there, measure that external part. All right, so what do you guys think? So if you're thinking this is going to be similar to our last theorem, you are correct, because this number times that number is going to equal this number times that number. All right, big surprise. I know, so let's calculate that. Let's make sure. This times that, 93.72. This times this, calculate. that times that, and voila, 93.72. And of course, we can adjust this lengths, right? And notice how, as I move this, that number doesn't change, right? This product is always a constant as long as the other one's fixed. But if I move this external point, that's when things start changing. Pretty cool, very cool. All right, so there we go. We've seen the relationship for our second theorem. Let's get that down in writing. Screen mirroring, zoom. And I think I wrote this one down earlier as well. Let me just make sure. If two secants intersect outside the circle, then I'm sure you guys could figure out a way to write it down. But here's the way I wrote it. The product of the measures of one secant segment. So one secant segment. Here we go. Let's call that AB. So the product, so AB times, so one more time, the product of the measures of one secant segment, there's my secant segment, and its external segment, so let's call this external segment, BC, right? So AB times BC equals the other one. So the other one, let's call this DB, let's call that point E, and so that's going to equal the entire other secant, which is DB, right, times the external portion, which is ED. All right, so there is our second theorem. And I'm actually going to copy and paste this diagram too for our second theorem. Here is the fun proof now. All right. And I think I did not label this the same way. So given secants ABC, so let me redraw this. ABC. How did I do that? All right, A is going to be on the outside. So A, B, C, and A, D, E. Intersect at point A outside circle O. All right, that looks good. We're going to prove, all right, entire secant AC, right, times the external portion, BA equals AE times AD. All right. So again, just like how we analyzed the last proof, right? We see we have a product equals a product, right? Which means, only time we've done that, product of means equals product of extremes. So again, we need some similar triangles. So if you set up that proportion, you can figure out which triangles you need to draw. The triangles we are going to be needing are these ones, this and that. So the triangles we want to prove similar are this triangle and the other one. Don't want to, right, they overlap, so it's kind of hard to see, but we want to prove those two triangles similar. You might be thinking, oh, this looks pretty congruent to me, right? But that's not what we're trying to do. We're trying to prove them similar. So how can we do this? Well, let's get started. Start at step 2. Step 1 is the givens. Step 2, we're going to do our constructions again. All right, same reason as before. Construct chord CD and EB. Construct CD and EB. All right, step 3. Now we want to prove those triangles similar. So we got to prove angles similar. Right, we did all our angle theorems already. So what we want to be looking for is some inscribed angles. So I see, here's an inscribed angle. Right there, angle C. Angle E is an inscribed angle, and they both intercept the same arc. So therefore, they must be congruent. So angle C is congruent to angle E. So we got one pair of angles congruent. And same reason as over here, right? Inscribed angles that intercept the same arc or congruent. I see what I did. I just left out a word. That intercept the same arc or congruent, right? So same reason. Here, of course, right, we got, again, two angles that intercept the same arc. And so what is our angle is going to be congruent in these triangles? Well, we got these angles, but I don't really know how to prove those congruent, right? We've never done a chord secant theorem, so that's out of the picture. But they all also both share angle A, and so we can say angle A is congruent to angle A, reflexive property, right? We've got enough to prove those two triangles similar, and then set up the proportion, product of means equals product of extremes. So I guess I'll finish it up, but from here, it should be a piece of cake. Triangle ACD is now similar to triangle, let's just make sure we name this correctly, ACD AEB. Right, angle, angle. Step 6, what's the proportion going to be? I'm just going to look at the final proof statement. So that's going to be AB over, AB is going to be here, AE has to be there, AD is going to be there, right? CSSTP, and then PO equals POM, AC times AB equals AE times AD. Right, so these are not difficult proofs. And right, they all, again, boil down to just a similar triangle proof, which we've done many, many times. Except now we're doing it in circles. So these are nice proofs, right? They combine a lot of good stuff, but not very hard. All right, this example down here, this is a lot better than example 1. So pause the video and give this a shot. Right, I'm going to copy this down here so I can label every day. So we got AB is 3, AC is 8, DE is 2 less than AD. So DE, this guy, is 2 less than AD. So if I call AD, let's say, X, right? Then, what is that? DE is 2 less than that, so I'm going to call this piece X minus 2. All right, so this theorem says the entire secant, so let's start with the top secant. The entire secant has a length of 8 times the external portion, it's going to be 3. That's going to equal this entire secant, so be careful, we got to add X minus 2 and X, right? So that will have a total length of 2X minus 2. Equals 2X minus 2, entire secant times external portion, X, right? So let's distribute. 24 equals 2X squared minus 2X, and we got a good old quadratic, which you all learned how to solve last year and all remember how to solve 3 different ways by factoring, completing the square, and quadratic formula. Yes, guys? All right. So set this puppy equal to 0. And let's factor out a 2. You can also divide everything by 2 in an equation, right? You can divide both sides by 2, and that's fine. That'll keep the equation balanced. I like factoring out a 2. Doesn't matter how you do it. Factor out an X, sorry, a 2. We're left of that. How do we factor this? What multiplies to the middle term, which is -1, and adds to -12, right? That's going to be X minus 4 and X plus 3. Drop down to 2 equals 0. We use something called the zero product property, right? If we have 2 times something else equal to 0, well, think of it like 2 times A times B equals 0. If 2 times A times B equals 0, then don't you agree that this A has to be 0 or this B has to be 0, or they're both 0, right? So same idea here. We have 3 factors, 3 things multiplied by each other. So that means this X minus 4 has to equal 0, or that X plus 3 has to equal 0. And that is how we get solutions of 4 and -3. Do we have to reject either answer? Yes, we got to reject the -3 because when we plug that in, that don't work. So X equals 4. But wait, did I box that in too early? Yes, because this question asks you to find AE. So make sure you don't get too happy once you finish solving a quadratic equation. You still got to finish it up. AE is a length of 2x minus 2. So the AE is going to equal, what was x again? X was 4. 2 times 4 is 8, minus 2 is 6. And we can check if x were 4, I keep forgetting for some reason, right? Entire secant has a length of 6 times this length of 4 equals 8 times 3. Checks out. We're happy, and that is your final answer. All right, guys, so tomorrow we're going to be doing our last circle theorem. I know you guys are very sad. I will have a review post that goes over all the theorems we talked about as well. So that's going to be it for today. Enjoy the weekend. Happy Friday, guys, and see you guys later. Take care.